Vanakkam. Welcome to this video on biomedical instrumentation. We have been looking at various types of sensors. We looked at various sensors: resistive, capacitive, inductive, LVDTs, piezoelectric, optical, chemical, chemfets, biofets, etc. In this video, we will focus our attention on Hall effect sensors. Essentially, the principle of operation is that when there is a magnetic field that is present, these sensors, or the Hall effect sensors, essentially transduce these magnetic fields into potential differences or voltages by using Hall effect. But then, what is the Hall effect? Hall effect is the effect where a current carrying conductor develops a transverse electric potential that is proportional to an applied magnetic field that is orthogonal or perpendicular to that magnetic field. Let me connect the battery. So we were telling what the Hall effect is. It's a situation in which a current carrying conductor develops a transverse potential, electric potential, that is applied perpendicular to a magnetic field, to an orthogonal magnetic field. These are extraordinarily compact or small size sensors. They are compatible with the CMOS devices, and they are extremely low voltage devices. And so they are used, they are extremely low power devices. So they are quite often used in biomedical applications. Suppose, and what are the various applications? For example, we are interested in magnetic immunoassays, or single cell MNP profiling, or measuring pulse wave velocity in arteries, for example, or flowmetry in blood vessels, for example, or how do you control injection, rate of injection in a syringe, for example. In all these cases, Hall effect sensors are used. They are also used for measuring displacements using this principle. So essentially, what is this principle? Electromagnetic induction. So the force in a closed loop is directly proportional to the rate of change of the flux. So in this case, this voltage is a function of J, B, and RH. The advantages of these are that they are extraordinarily sensitive. They are quite often used in biomedical applications because they are non-contact and they are immune to electromagnetic interference. They are highly sensitive and very reliable, and they can be used in the harsh environments, and they are highly compact, highly rugged, and suitable for integration into micro devices. So they can go in as part of a larger system. Quite often they are used in blood flow meters, measuring pulse wave velocity, arterial pulse wave velocity. Sometimes they are used to measure position sensing in prosthetic limbs and to detect motion, muscle movements, for example. What are some of the key design considerations? You need to decide sensitivity versus noise, because high carrier mobility and low sheet resistance and differential architectures, sometimes we can take advantage of these principles to improve sensitivity while keeping the noise minimal. The other consideration is to use hermetic encapsulation, similar to the type that we discussed in, where did we discuss this previously? Hermetic encapsulation. We discussed that while discussing LVDTs. So for example, we can use PMMA, parylene, and other such materials to completely shield the electronics from the biofluids while maintaining sub-micron distance from the magnetic levels. That way, because we are measuring magnetic sensitivity, is it not? So that way, the core measuring system will not be exposed to the biofluids whose properties it is measuring. We can also decide between whether we need to use AC excitation or DC excitation for this effect. So if we can find or design a lock-in amplifier, for example, that's a huge challenge. We can do lock-in detection, then you can maximize signal to noise ratio so that you could measure changes that are at the resolution of 1 microtesla or less, for example. And this can be integrated into microfluidic devices such as on-chip, lab-on-chip type of coils, lab-on-chip type of devices, for example. So these are versatile devices that can be integrated, that can be used as a standalone biosensing devices, or can be integrated into a larger biosensing module, or can serve as the input system for a larger control system, for example. So these are all used in automated lab-on-chip devices and high throughput device systems, and also quite often they are used in implants and wearable systems. Of course, the future looks at nanostructures, nano-sized devices, wireless devices, self-powered or battery-less devices, and AI-driven signal processing, and multimodal platforms. So with this, we come to the end of the discussion on Hall effect sensors. And in summary, these are the various topics that we discussed in this week's videos. Resistive sensors such as strain gauges and thermistors, those that are used to measure strain, displacements, and change in temperature via resistance. Capacitive sensors, quite often used to measure displacements and pressure differences or forces in some cases. Inductive sensors, most important of this, we had a long discussion on LVDT that uses change in inductance to measure force or displacement. And piezoelectric devices that converts mechanical force into voltage, applied pressure into voltage. Electromagnetic devices are Hall effect principles, Hall effect sensors, and, electrochemical devices, ion selective sensors, or zirconia-based gas analyzers, or optical sensors, those that have an LED and a detector that are used in non-invasive application, for example, to measure oxygen saturation, etc. With this, we come to the end of this video. With this, we also come to the end of this week's content. Thank you very much for your attention, and I look forward to interacting with you through the forum. Please keep the forum active, and those who have not registered for the exam, please do register for the exam as soon as possible. My best wishes. Because when you commit to writing the exam, you will actually invest the time in preparing for the exam and invest the time in learning the content. If you say, let me decide whether to write the exam or I will simply watch the videos, there will be other videos that take over precedence over biomedical instrumentation videos. So please do commit yourself to writing the exam. My best wishes. All the best. Please do register for the exam. I look forward to interacting with you in the course forum. Thank you very much.